Doctor,
Yeah.
we are very happy for having you here, and thank you for the acceptance to this event. This is our first international event, and it's an honor. You are our first speaker.
Thank you so much.
Thank you. Juve, ¿podemos comenzar?
Sí, sí, claro. So, welcome, Johander, Doctor. Dr. Johander Singh is currently working as assistant professor in the Department of Chemical Engineering of the Standard Balabni National Institute of Technology, Surat, SBN IT, Surat, in India. After completing his PhD from Indian Institute of Technology in Delhi, IIT Delhi, he worked in Tecnológico de Monterrey, Mexico, as postdoctoral researcher. His research interests include process intensification, heat transfer, and fluid flow, microfluids, microflow, extraction process, separation process, CFD, modeling and simulation, industrial safety, and hazard management. He has published several papers in peer-reviewed international journals and international conferences of repute. He has selected for National Doctoral Fellowship, All India Council for Technical Education Governance of India, for proposing his PhD in fields of process intensification. Only top 50 PhD students for all over country are selected are selected for NFT. Every year, Dr. Singh has also selected a member or SNI candidate level in 2018 for his research contribution by Sistema Nacional de Investigadores in Mexico. Currently, he is handling research project, continuous and sustainable extraction of critical metals from e-waste, funded by Ministry of Education, Modi East Government of India. Okay, it's a very pleasure to have a conference with you, Dr. Johander. You have only 45 minutes to make your speech, and I don't know if you have any question, Dr. Johander. Mr. Johander.
Al parecer está teniendo problemas.
Oh, okay.
Con su red.
Creo que ya se desconectó.
Sí, parecía que sí tenía uno que otro problema de conexión.
Hello. Is my presentation visible?
Yes. Yes, it is.
Is it visible?
Yes, it's
Yes. Yeah.
Okay.
Go ahead.
So thank you very much for the elaborate introduction. Shall I start?
That's okay. Dr. Kender, you have only 40 minutes, maybe 45 minutes to make your presentation, please.
Okay.
So
Okay.
let's go. Go ahead.
Fine. Thank you. So thank you very much once again for having me here in the first international conference organized by TESCO. So my presentation basically will cover, we'll cover a topic known as energy efficient device for process intensification and their advantages and challenges. Okay, so basically we'll start with the process intensification, and then we'll see the application of real life application of process intensification in heat exchangers. Okay, so trying to make it full screen. I think now it is working. Is it full screen now? Okay, so I'll start with the introduction of my institute, and this is just a request to you people. Please let me know if I am audible or not. Whenever you're losing voice, please let me know. I'll try to reconnect. Okay. So my institute, it is situated in a city known as Surat, and Surat is known as the city of the diamonds because there are a lot of merchants which extract diamonds here and sell them all around the world. And the Surat is the 8th largest city of the India, and it is a very beautiful city. As you can see, there is a river Tapi which is flowing in center of the city, and both the side of the rivers, this city, the people are situated here. And our institute, which is known as Sardar Vallabhbhai National Institute of Technology, it is situated here, and it's a very beautiful campus with a lot of greenery and facilities here. And this is our department, Department of Chemical Engineering, and this is one of the lecture hall, so here almost at a time thousands of students can study in this lecture hall. It's very beautiful, very big, and occupied with the world-class latest facilities. And we have been using this since the COVID-19 started. We have been using it for online classes in our institute. For all the courses like Bachelor of Engineering, Master of Engineering, and the PhD people. Okay, I think I would not take more time on this. I would start with my topic. So process intensification. Process intensification, how to define process intensification? So process intensification, whenever we think about a product, we basically start with the raw material, and we just think about product. We do not, start it back that if we have a raw material, we would like to have a product, and that's it. We will not think about the environment. We will not think that how much we can save, or we will not think about the process if it can be improved. So process intensification is a concept which includes all these things in one process. So by process intensification, we can actually reduce the capital cost. We can improve the safety or inherent safety of that particular product or particular device. Also, we can improve the production efficiency. So basically, process intensification, if we include two steps here, we include, let us say, in between the raw material and the product, we include some concepts of green chemistry and the process intensification. We can actually save our environment. Same times, we can make novel products for our survivals. So in green chemistry or green engineering, everybody knows that what are different concepts. The concepts are like we should have zero waste, and we should use green solvent for making some new chemicals or supported catalyst or higher reaction rates. Okay, but what steps are included in process intensification, or what we can achieve by this process intensification? So process intensification can help us basically to reduce the residence time or minimize the downstream separation, and to reduce the energy consumed, and to reduce the waste, even make it up to zero, and low inventory, improved inherent safety of the process for the people working in the plant and the people who are consuming the final product, the finished product. Okay. So for this concept of process intensification, we will study a new device known as Coil flow inverter here. And this Coil flow inverter, how we developed this, I will start with that, and why it was needed. I will also explain that. Basically, this coil flow inverter for this particular lecture, we will keep it up to the heat exchanger applications. And we know that in heat exchanger applications or in heat transfer devices, how one can increase the heat transfer coefficient. That is our aim in heat exchanger. So in industry, whenever we use a heat exchanger, we want to have more and more heat transfer so that we can, cool down our product or raw material or quickly, or we can increase the temperature of raw material up to the reaction temperature. So for that purpose, many of the technologies have been used. For example, this artificial wall roughness, okay, porous wall, fine grooves, that dimples, or you can see something like this, that these are tube inserts. So in the tube insert, when you use some kind of, let us say, strip, and you insert it inside the tube of a cell and tube heat exchanger, and this tube insert, what it will do, it will increase the chaotic advection inside that tube and somehow enhance the mixing. Okay, now the next step in this process, to enhance or to intensify the process of mixing inside the tube of the heat exchanger, people have tried a lot of different devices like a spiral coil tube. And why spiral coil tube, that I will be explaining here, or helical coil tube. So why spiral or helical coil tube? Because of this structure we see here in the picture down in the slide. So if you see here, you have this kind of structure. This is a spiral coil tube, and if you have, let us say, this is the inlet, okay, and flow of fluid insert here. So what will happen in the vertical direction of this vertical outward direction, centrifugal force will act. Okay, so let us say this is the outward wall, this is the inner wall, and if you see here as the like this is inner wall and this is outer wall. So what will happen, this centrifugal force, which is acting normally outward toward this tube, it will try to pull this fluid from center of the tube towards the wall, and this fluid, which is traveling from center to the wall, it will hit the wall here and bifurcate in two directions. Okay, so it has bifurcated in two directions. And now this type of concept was very first introduced by the very renowned scientist known as Dean. So Dean has invented that kind of concept, and he actually used these kind of spiral coil tube for inventing this kind of chaotic type of structure. What is happening because of this structure? Now, once this fluid is striking here and this fluid is moving back, so this is called flow inversion. This flow inversion is actually increasing chaotic force inside this tube, and hence the gradient of the temperature or the velocity inside this tube is decreasing, and so that more heat can transfer from the outside. And similar is the case of this helical coil tube. Okay, so here also we can see fluid is entering from here. This is the entrance, and it flows like this. Outward normal forces, that is centrifugal forces, acting like this. So again, this kind of structure will happen there. Now we thought, if let us say this concept of Dean vortices or Dean force, if we can extend it to the flow inversion, can we improve this mixing process or heat transfer process more? So we started with this device known as Coil flow inverter, and if I hope you can see that this is the inlet here, and we started curving this tube on a bigger diameter tube here, like this, and we then change the direction of the flow by changing this tube. So by an angle we have modified this structure. So if you can see this angle, we kept 90 degree. Why we kept it 90 degree, I will tell in my further slides. So if you can see that this kind of structure will happen. Okay, and these these square tubes, we called it baffle, and these are the tubes. Okay, and you can see that inside tube diameter is noted by dt, and the center to center distance between the two consecutive tubes is known as pitch, that is noted by p. This is the similar concept which is used in cell and tube heat exchanger, and this is acting as baffle. So what will happen? So after this, let us say fluid is entering from here. Okay, and we know that the direction of the centrifugal force is outward normal of the flow, direction of the flow. I mean, here also it will be outward normal. Now if you see at the end of this first band, we'll call it that we are having one band here, so we'll call it first band. After this, the structure of this D vortices would be like this. So since we take it from here, this force will pull it down, pull it towards the wall, and it will strike at the wall and then bifurcate into two directions. So that kind of structure will appear there. Okay, so this is after first band. Now we have changed the direction of centrifugal force by bending it at 90 degree. So centrifugal force here, it was horizontally working. Now it is acting in normal direction. So because of the change of centrifugal force, now the direction of the force or the flow will also change. So initially it was like this after first band in horizontal direction. Now it is in vertical direction. So you see what will happen because of this. The places where this mixing was not there in this picture, you can see here. Now those places are also having very good mixing. So because of this flow inversion, we are having very good mixing here, very good mixing here, and that will increase the mixing inside this tube, also reduce the gradient inside that tube. And same thing will keep happening after each and every band. So this is, let us say, first band, this is after second band, this is after third band, and then the at outlet. Okay, and these all things are happening here, which I have already explained. So we tried with this kind of geometry, which nobody did actually, and we tried with heat exchanger applications that I'll be explaining in few of the slides. So how we optimize the 90-degree angle, that was I was talking a few slides earlier. So we started with many of the angles, like hit and trial in the lab, that which one would give us the better performance. And we have not started it as an heat exchanger device. We were thinking that this device will work as a very good reactor because we are having very good mixing. So we started with RTD studies, and we started with different different kind of arrangements here, if you can see that. And then we come to the conclusion after many of that kind of arrangements, that 90-degree angle is providing us the best mixing here. And that how we are seeing that best mixing, we have done a lot of studies in terms of RTD, also in terms of heat transfer, and we come to the conclusion that 90 degrees providing the best mixing and best heat transfer performance. So that's why we say that 90 degrees is the optimum angle for this kind of flow inversion in the passive devices. Okay. So with that concept, first we did this at a laboratory scale, and then we come to the concept of once we establish the device on the laboratory scales, we wrote to the ministry here in India, and they have provided some fund at IIT Delhi during my PhD. So we developed this pilot plant there in IIT Delhi. And in this pilot plant, we have installed this device, which is known as Coil flow inverter. And this is how it looks there. I mean, this is this you can easily recognize that this is kind of cell for any cell and tube heat exchanger. And this is the tube bundle. In cell and tube heat exchanger, we have straight tube bundles or U-tube type of tubes bundle there. But in this type, you can see that we have rounded off a tube over this another tube. Okay, so this tube is acting as a baffle, and this square baffle is very beneficial while flow is there in cell side, because it will bifurcate the fluid. Okay, and this straight rod between these bank. Okay, so this type of one arrangement, like one arrangement or this one, it is known as one bank. Okay, so this this one bank, it is again connected with some circular baffle. So this baffle, it has a different arrangement of flow arrangement, flow in cell side. So this has a baffle cut in, let us see, if this first bank, this baffle has a baffle cut here, then for second bank, it is having in opposite direction. So basically it is diverting fluid inside that cell, so that there is no channeling or loss of mixing is happening in the cell side. Okay, so that's what that was ensured there. And now, if I explain, this is the pilot plant working seat there. So this picture here is showing the 8-bank heat exchanger there, 8-bank coil flow inverter heat exchanger. And these are different arrangement here. This is basically air compressor to just test for let us say if this side in the tube side, air is going at 204 degrees Celsius, and how much length or how much bank it is taking to come up to reduce a temperature up to 37 or 31 or 32 degrees Celsius, like that. So we noted down in case of let us say if we have air in tube side and cooling water in cell side, which is cooling water is going from, let us say, here. Okay, so this cooling water is going from the bottom. It is across. I mean, it is a counter flow arrangement. Okay, so here you see this fluid, this air is entering at 204 degrees Celsius, and within one bank, that is 0.022 meter square. Surface area here is 0.022 meter square. Within this much less area, this is reducing temperature from 204 degrees Celsius to 37.7 degrees Celsius. So that means that all other these banks here, these are useless. We really don't need these banks here, because this is additional cost. If we can reduce temperature, let us say from 204 to 37 in first bank itself, we really don't need that big device for this. But for safety, we can keep, let us say, 2 bank here, and we can try with more experiment and generate more data and results to be sure that it will be working in the same fashion or not. So this is what I was talking about. And then here, that 204 to 31 degrees Celsius, it is coming into within an area of 0.44 meters square, which is 2 bank. Okay, so 31.3, and after that is pretty much constant. There is no change at all. So we thought that why we should use 8-bank heat exchanger. We can try with a lower area, with a lower number of banks. So we installed 3 more heat exchanger in our pilot plant. This is a 4-bank heat exchanger. This is a 2-bank heat exchanger, and this is a 1-bank heat exchanger. Okay, so we installed this, and we repeated all the experiment which we did with 8-bank heat exchanger here. Okay, with 2-bank, with 1-bank, and 4-bank heat exchanger, and then we compared the results. So let me just give you an idea that how 8-bank heat exchanger, how big this 8-bank heat exchanger look like, and how big this 2-bank heat exchanger will be looking like. So if you see this left right hand side picture here, this is 8-bank. This is what we call a 1-bank. So 1, 2, 3, 4, 5, 6, 7, and 8. So till the end, we have 8-bank here. It looks like a huge device here. And after that, we reduce it up to, let us say, 2-bank here. So this is a cell of the 2-bank, and this is 1-bank here, of course, without the baffles here. And this will be the 2-bank device like. So you can see that it is almost 1/4 of the footprint it is taking. It is very less in footprint, 1/4 times less. And we just wanted to test it whether it is giving the same results or not. Okay, So this is again the experimental setup of pilot plant. We started with I told you earlier that we installed these three new devices. So this is 4 bank, this is 2 bank, as you can see 1, 2, and this is 1 bank heat exchanger. And we installed this air compressor here just for hot airflow. And we have 2 heaters here. One is water heater, one is air heater. We have 2 loop basically. So primary loop is basically for air water system. Okay. So we have tested, in our case, we have tested 4 different arrangement. We kept hot air in the tube side, and then cold water in the cell side. We kept hot water in the tube side and hot water in the cell side. Also, we tested this device for hot water in tube side and cold air in cell side, which is the worst case, and for air system. Okay, so this is primary loop here. We have air. We will heat up this air up to the desired temperature by this air preheater, and then this heated air will go into the tube side. And from the cooling tower, this cold water will be entering to the these heat exchange. Okay, in all these three, I mean the 4 bank, the 2 bank, and the 1 bank heat exchanger. Okay, and this secondary loop, it is basically having some cell side loop. So in cell side, this air will go through the blowers or the water from this water reservoir. Okay, so this is very well explained. Now, this is what I was talking about, the process conditions, that we used water in tube and cooling water in cell side, then hot water in tube, ambient air in cell side. And these were the flow rates for these different type of flow arrangements. So flow arrangement for water, we kept it 50 to 300 kg per hour, which is pretty much higher, to just test it at the higher flow rates so that we can make some industrial standards. Then the pressure, which was inside those tubes, 1 to 5 kg per centimeter square, and this is the temperature here. Okay, so temperature we varied here in case of water in tube side, 80 to 120 degrees Celsius. In case of compressed air in tube side, we raised the temperature. We varied the temperature from 80 to 230 degrees Celsius. So this is again to understand that how the flow was taking place. So the hot fluid was coming from the top inside the tube, and cold fluid was going from the bottom, and that's how it was a cross. The flow arrangement was there. Okay, and this 1, 2, 3, 4, 5 for design perspective, you can just note down that this whole arrangement, we are calling it coil flow inverter tube. Okay, this blue color, this is the coil flow inverter tube. And this second, which was like in a circular plate, it is known as cut plate. Also, it acts as a baffle. Now the third one, it is a square shaped baffle around which we have, rounded this tube, and this straight rod, it is to give strength to the whole structure. Also, it is acting as a baffle, and then this fifth one is acting as a cell. So this is how we made this device. We have designed this device, then we have really constructed, and then we have conducted experiment in the pilot plant scale. First on the lab scale, I myself conducted approximately 864 experiments on these 4 devices just to compare their performances. And as you know that for any kind of heat transfer experiments, we need to make balances between tube side and the cell side. This is the very, very important but basic law of heat transfer. Okay, so we must have this Q in tube side should be equal to Q in cell side. Then only you can note down all other readings like temperatures and all, and then you can go and calculate heat transfer coefficient. Okay, so here if you see this for 1 bank, 2 bank, and 4 bank here. So in 1 bank CFI, for this much tube side flow rate, 53.8 kg per hour of flow rate, this Q here in tube side is 1673.18. and Q, that is heat flux. In cell side, it is 1609.20, which is pretty much the same value. If you want to find out the percentage difference, it will be very less. So we thought that now we have achieved a steady state condition. Now we can note down the reading. So we can note down the inlet temperature of the fluid and outlet temperature of the fluid here, and then we can make different calculations. Similarly, you can see for 2 bank, it is 2921. Here it is 2806, and for 4 bank 3043, and here it is approximately 3000. So both are the approximately same value, so we can take values. So this heat balance is very much important. Okay, now for water system, this is the flow rate we kept 250, and temperature were 80 degrees Celsius. That is the tube side temperature, that is inlet temperature, and cell side flow rate was 1500. This is just one reading I'm trying to explain here, that how we calculated, how we made the calculation part. And in tube side, we took the hot fluid. In cell side, we took the cold fluid of water. And then you can see these different experiment numbers. We basically, to track down that from which experiment we have taken this data, we gave them some definite experiment number there. So this is for 1 bank, 2 bank, and 4 bank. Different banks we have compared, and we tried to use the data which is taken at steady state from the previous slides. And then we calculated this delta T log mean temperature difference, which is pretty much the same which we do in heat transfer course. Okay, so we basically calculated that in case of this counter flow arrangement, and then we calculated overall heat transfer coefficient. So now if I see these conditions are same for all these 3 different experiments for different devices, and if we see the overall heat transfer coefficient here, the overall heat transfer coefficient for 1 bank heat exchanger is approximately 800, while for 2 bank and 4 bank it is approximately 880 watt per meter square degree Celsius. Okay, so in this case we can see that in 1 bank heat exchanger, the heat transfer performance is little bit lower as compared to the 2 bank or 4 bank heat exchanger. We are not comparing at all 8 bank heat exchanger, since we know that the heat transfer coefficient is going to be the same. We have already compared in the next figure that I'll tell you. Okay, and we will have a lot of extra cost in terms of extra material which is used to make that particular bigger device. Okay, so now we try to compare the overall heat transfer coefficient. I know that this slide is a little busy, but try to pay attention with me. And this overall heat transfer coefficient on y-axis, this is mass flow rate inside the tube in kg per hour. Okay, inside the tube of heat exchanger, and we try to compare our results of our device, that is CFI heat exchanger, CFI HE we are calling it, and we took different bank, that is 8 bank, 4 bank, 2 bank, and 1 bank. And 8 bank heat exchanger, the surface area for 8 bank heat exchanger is 1.76 meters square. Okay, for 4 bank heat exchanger, surface area is just half of that, that is 0.88 meters square. And for 2 bank, it is 0.44 meters square. For 1 bank, it is 0.22 meters square. Okay, and then we also took this plate type heat exchanger of 1.76 meters square, that is equal to the 8 bank heat exchanger. Okay, and then we also took some data for cell and tube heat exchanger. So these all heat exchanger were installed in our pilot plant. We installed PHE, we installed SHE, we conducted experiment, and we took this data ourselves. Okay, so this is not we have taken it from somewhere else, this is our data. So now if we try to analyze this figure here, if you see this at so here you can actually try to analyze the effect of 3 different parameters. One is tube side flow rate. Okay, the second one is the effect of cell side flow rate, how it is affecting heat transfer. And third one is the effect of geometry, effect of the different design of the heat exchanger. So different design I mean is this PHE, SHE, and then these coil flow inverter heat exchanger, whether it is 2-bank, whether it is 4-bank or 8-bank heat exchangers. So now if I try to see, I can easily visualize that if we are increasing, let us say, cell side flow rate, this MS. So this is 800 kg per hour here, 800 kg per hour, and these pink color, it is 1300 kg per hour. Okay, so this is 1300 kg per hour, this is 800 kg per hour, and in case of CFI here, this is also 800 kg per hour. So we can see huge effect of the cell side flow rate in the performance of coiled flow inverter heat exchanger in cell and tube, in cell side flow rate. Okay, so basically we mean to say here is that if we are increasing cell side flow rate, okay, so cell side flow rate, if we are increasing, we will see a drastic change. I mean, drastic increase in the overall heat transfer coefficient of coiled flow inverter. So this is basically for all 8, 4, 1, 2 bank heat exchanger. That is for 800 kg per hour of cell side flow rate. This is for 2000 kg per hour of cell side, and you can see that it is approximately twofold increase in the, I mean, more than twofold increase in the overall heat transfer coefficient with increase in the cell side flow rate. Now, if you check the effect of the tube side flow rate, you can see in all the devices, the heat transfer coefficient is increasing with increase in the tube side flow rate. Okay, which is, we know that if we change the tube side flow rate little bit, it will very significantly change the heat transfer coefficient. You can see there that these kind of switches are there. Okay, and now if we see that this 2-bank heat exchanger here, 2-bank heat exchanger, and we compare at the same condition of cell side flow rate 800 degree, 800 kg per hour here, 2-bank 800 kg per hour. So this blue triangle with this blue star here, you can see that this coiled flow inverter with the same heat transfer area is giving very high heat transfer performance. Okay, however, here you see the area is very less as compared to the PHE here. And of course, SHE is less than the PHE itself, because PHE is having much more higher heat transfer surface area, I mean higher heat transfer coefficient, which is very much proved in the books. So even our device is having better than the PHE. Now, this experiment was for hot water in tube side and cold water in cell side. We repeated the same experiment for different arrangement of the fluids. So we took hot water tube side here, and we cool it down with the air in the cell side, and there also we are getting very good result in terms of the 2-bank heat exchanger, which is providing us very I mean similar heat transfer coefficient as it is provided by 8-bank heat exchanger or 4-bank heat exchanger. So then again we repeated the experiments for hot air in tube side, cold water in cell side. Again we are getting the similar kind of result. Even the worst arrangement, which is air cooled by air, okay, hot air cooled by air. So there also the performance is the same for 2-bank heat exchanger. You can see it here. Okay, and then we are seeing that the effect of these different pressure of the air, which is negligible. Air actually doesn't have much effect. However, this flow rate, mass flow rate on the cell side, it has an effect, which is already explained in case of the first case, that is hot water in tube side and cold water in the cell side. Now, since it is increasing the heat transfer coefficient drastically, we wanted to check whether we are losing very much in terms of pressure drop, and we try to plot in terms of pressure drop here, and also we calculate in terms of friction factor here. So if you see this picture in the left hand side, you can see that 2-bank heat exchanger, which is this one, 2-bank CFI heat exchanger, which is 0.44 meters square. It has approximately same pressure drop to that of 1.76 meters square of PHE and SHE. However, we have already seen that it is providing very much higher heat transfer coefficient as compared to SHE and PHD. And the simple reason behind that is basically the coiotic advection, which we are achieving due to that mixing process, enhanced mixing process inside the tube by coiotic advection there. Okay, and similar is the case of this friction factor with the Reynolds number here. Friction factor, we can see that it always decreases with the Reynolds number. This is a very well known factor. Within Asia, it is basically decreases. And you can see here also this 2-bank heat exchanger or 1-bank heat exchanger. These are having the similar kind of friction factor here. Okay, so we noted down that 2-bank CFI heat exchanger, it is having approximately 60% lower pressure drop as compared to this 8-bank heat exchanger. At the same time, we are having say approximately the similar performance in terms of heat transfer coefficient. Okay. Also, friction factor here, it is found lower than that of 8-bank heat exchanger. You can see here is very high, and here it is approximately, you can say, 60% lower. So 2-bank, we can say that we can make these conclusions from here that this 2-bank heat exchanger, it provides the same overall heat transfer coefficient, while the pressure drop or the friction factor also is lower by 60%. Okay, and we have also noted down that CFI heat exchanger provide higher heat transfer coefficient as compared to the traditional or the conventional heat exchanger like cell and tube heat exchanger or platen form heat exchanger, and it was as high as 4 times. And you can see that the surface area was very low. I mean, surface area in case of SHE and PHE was 1.76 meters square, and in case of coil flow inverter, the surface area was very less, like 0.44 meters square if you're talking about 2-bank heat exchanger. Okay, so also very important thing what we noted down from our experiments from all 4 devices, that we can reduce the size of our device up to 4 times. Okay, so that is a great thing. We will be saving a lot of money in terms of material cost, also in terms of pumping, because we have less area now. We have to pump, we have to spend less energy to pump the fluid inside these tubes or the cell. So basically this was a big achievement which comes out through these experiments. I have tried to explain it briefly, but if you have any question here at the end of this section, I would be happy to answer, or else I'll continue with this nanofluid flow in coil flow inverter. So anybody, if you have any question from the previous portion, I would be happy to answer. Yeah, am I audible, Dr. Julio?
Yeah, I think nobody.
I should continue.
Yeah, please.
Yeah. Okay, fine. So now we tested this device with the standard fluid, which is like water or air, which is very much used in industry. So we thought that part is already done. Now we thought that people are very much worried about cooling down these electronic devices. Okay, and they are using different kind of fluid, different kind of devices there. Now can we make some kind of combination of, let us say, this flow inversion with the nanofluids, so that we can reduce the heat transfer coefficient, or we can remove that heat from that electronic circuit, and same time we can use some new kind of fluid which is always helpful in removing this okay. Yeah, so we fine. In the chat I received a message from doctor to finish the presentation. So it's okay. I will stop here and I will try to answer the question.
Yeah, the question is, what is the estimated cost about process?
Yes. So this particular pilot plant, we got a funding of around uh, uh, if we talk in Mexican currency, it would be around 1 million.
Okay. Maybe in dollars, it's okay.
Yeah, fine. So this funding was around around 1 million from the government to make the building and the entire structure of the pilot plant and all. And we designed this heat exchange by ourselves, so we didn't need to pay to anybody else. But for construction and material, we paid a huge amount for this device because it was made very first time. But when we compare the cost with the silent tube and plate type heat exchanger, if manufacturing cost, so manufacturing cost, it is initially higher, that we have to admit, because in plate and frame heat exchanger, it is coming a little higher. Though I do not have real data, but it is a little higher as compared to plate and type heat exchanger or cell and tube heat exchanger while we are making. But I think in terms of the results, we are getting very good results, so that so we can go for this kind of heat exchanger, and we can further study to reduce down the cost. I mean, that part we can do.
Yeah, I know. I have another question for here. What is the
Yes.
greatest benefit of this process?
See, in terms of so if you allow me, I'll go to my last slide. I wanted to discuss here, but I couldn't because. So we have tried this device in many of the application. We tried it as a micro heat exchanger. We tried it as a. So you can see this slide here. I hope you can see this. So these are the different application of this particular one single devices here. We have published in many different journals. Also, what we did is we approached one of the industry here to apply in real-time application in one of the fertilizer industry in India. If you type in Google Cribico is one of the fertilizer industry in India. So they installed it in their bypass line, not in the process line, and they are just further studying by themselves, because industry people doesn't believe easily, especially the academic researcher. So they are testing it, and they are saying that the results are good and it can be used at heat exchanger, but we do not want to disturb our process. So that kind of response we got from one of the industry where we approached, but we are approaching more industry. And in terms of applications, you can see, as you said, the biggest advantage is in terms of mixing. Since mixing tube side mixing, that is radial mixing, we have increased it higher than any other such passive devices. So this mixing is actually increasing our heat transfer coefficient, our mass transfer inside the tube. So now it is actually increasing the reaction also. So one of my colleague, Dr. Enrique, he tested this device for photochemical reactions in Tecnológico de Monterrey, and he has reported very good results. So the biggest advantage of this device, I would say, is its application in various areas.
Yeah.
And we can actually explore more. I mean, we should not, stop ourselves up to here. We can explore whether this device is actually working in that for microreactor or not for extraction. I mean, this particular paper was published by Kurt. This study is from, I guess, one of the university from Netherlands, and they use this device for metal extraction, this continuous metal extraction. You can imagine how important it is now to remove those harmful metals from the environment. Or let us say, if you have waste waste metal in terms of the processors or electronic devices, or waste from industry like waste catalyst. So they have tried to use this device as a continuous extractor, and they reported very good results there. So it's a very big, beneficial device. But of course, we need to test it at pilot plant scale, as we did in case of heat transfer. I mean, it is these are just the lab skill studies.
Okay, that's good. And we have a final question. Which the
Okay.
most difficult part of starting using this method?
Okay, so the difficult part is to start with the design. I mean, for each type of the applications, the design is not going to the same. I mean, you will have to change. For example, for metal extraction, you required very low flow rates. This metal extraction, if you increase flow rates like very high, then metal extraction would not be happening. So first of all, the most important part is that you design this device according to the need of the process which we are going to perform. Okay, and then after that, construction. I mean, no other industry. We need to find industry or the vendor who can make these kind of devices for us. Of course, we cannot make it. We can make a lab scale device, but not pilot plant scale. So that kind of the challenges are there, and those challenges we have to face when we were going for this pilot plant scale. And we were fortunate enough that we found one industry to make those kind of devices for us. So they have design. I mean, design was our, but they have made all the devices for us. So that is after that. The experimentation part is very simple, because a simple heat transfer experiment which you can do in your lab using some simple cell and tube heat exchanger. One fluid is going inside the tube, and fluid is going outside in the cell side, and then you have different sensors to measure the flow rates and temperatures, and basically you go for calculation. So that part is very easy, but important part is you design it and then you construct the device itself.
Okay. A teacher here from Tesco says, Dr. Johender, congratulations for your explanation. This is very useful study of transport mechanics. Okay.
Thank you. Thank you.
So it's time. It's time. So
fine. Thank you. Thank you so much. And this occasion, I would like to thank Dr. Julio to give me an opportunity to be here and present. If anybody has any question, please contact to Dr. Julio. I am available. I will be able to reply.
Oh, thank you. Thank you. Thank you very much.
Thank you very much, Dr. Johender.
Okay.
Thank you, Julio.
Aquí en el chat de la reunión voy a dejarle a los asistentes, es para los asistentes, un formulario en Forms. Tienen que llenarlo y es más que nada para darnos una retroalimentación, para checar cómo se llama, qué estuvo bien, qué estuvo mal, qué podría mejorar. Entonces, de la manera más atenta le pido a todos los asistentes que lo llenen, ¿no? Aquí se los dejo. Ahí tienen que seleccionar la conferencia que acaban de escuchar. De hecho, es la primera. Inclusive trae los horarios para que no se equivoquen, ¿ok? No sé si gustan agregar algo, Tere, Julio.
No. Just I want to say again, thank you, Dr. Johender. It was an honor to having you here.
Yes, thank you. Thank you, Dr. Julio, for having me here and to interact again with my second country, which I say Mexico is my second country. So I had, thank you. Somebody has written in Hindi. Anyway, I have one question from Mr. Roll, I guess. What was the difficulty in measuring pressure drop? No difficulty at all. We had a sensor. If I can go back to the slide. So this was very, very well designed pilot plant. So we don't need to. Yeah, but in lab, in lab scale, you may have difficulties. So if you see here in this experimental setup, we have these pressure sensors everywhere to measure the pressure drop, to measure the pressure here. And then simply after, noting down these values, you can calculate pressure drop. So we have pressure sensors here. We have temperature sensors everywhere in this pilot plant. So it was not difficult at all. But yes, if in you're doing this study in lab scale, then you will have to, make arrangements for, let us say, maybe you can use rotameters if it is a lab scale experiments. And in rotameters, you can calculate pressure drop. I mean, you can calculate inlet and outlet, and then you can find out pressure drop.
Thank you, Doctor. We understand that this is a very exciting issue.
Yes.
The time is over.
Really, really
Yes.
exciting.
Thank you. Thank you so much.
Thank you, Doctor.
Okay.
Thank you. That's very intense.
Bye.
It's
Thank
great.
you.
Bye.
Bye-bye.
Gracias a todos, buen día.
Gracias.
Thank you, doctor. That is